Log on, tune in, find out. Another good idea from Cambridge.
Okay, well, first of all, let me thank the organizers for inviting me to give a talk before such a distinguished audience. Although my current affiliation is Oxford University, this is joint work with Oscar Garcia Prada in Madrid and Olivier Vicard in Paris. I'm going to talk the setting of this work is this correspondence between representations of surface groups into Hermitian D groups and solutions to Higgs equations. There have been two approaches to this, one of Higgs bundles by Roberto Garcia Prada Gotten and Undetti Riera, between others, and other of bounded cosmology by Berger, Jotzi, Binhar. In fact, 1 week ago, I think it was presented here a work in progress about the interplay by Harnik and Ott. I'm going to focus only on the Higgs bundle part. So a Higgs bundle, if we want to define it for a real non-compact semi-simple D group, we have to take its maximal compact subgroup, the Cartan decomposition of its Lie algebra, where H is the Lie algebra of that compact subgroup, and we have that M is this complement, this vector space. We consider the isotropy representation, and then we say that the G-Higgs bundle is a principal HC bundle, holomorphic, and a Higgs field is a section of this bundle associated to the isotropy representation tensor by the canonical bundle K. Okay, for instance, for the group SP2NR, we have that the maximal compact subgroup is a unitary group, and the joint representation is this sum of the second symmetric powers of the standard representation and its dual. So we'll have that the SP2NR Higgs bundle is a principal GLNC bundle together with a Higgs field. In this case, it has two parts, one is symmetric and its dual. We can translate this into a vector bundle language if we take a vector bundle, holomorphic vector bundle of rank m, and these two Higgs fields, we call them beta and gamma. Okay, now gamma is symmetric. Imagine by a moment that apart from being symmetric, it's also an isomorphism. So if we slightly modify this by taking a square root of the canonical bundle, we get something like this. And if we define W to be this V dual tensor of the square root, we have that gamma becomes a map like this from W dual to W, and it's some non-degenerate and symmetric. This is a metric on our bundle. So we could say that this W and gamma is a principal O and C bundle. And from the Higgs field beta, we can modify it in the same way. We do the composition with gamma to go from V dual to V dual, and at the end we get a Higgs field that goes from W to W tensor K square. We call it a K square twisted field. So we have obtained this nice object. So the question is, what's the relation between SP2 and R? Well, I should say before that this object happens to be a real GLMR Higgs pair. I put pair because we have that the field is twisted by K squared. What's the relation between SP2NR and GLNR? So the answer is in the Hermitian symmetric space SP2NR quotient by UN, and we could say that this GLNR is the non-compact dual of the isometry group of its Shiloh boundary, but we'll make sense of this later. But somehow I wanted to show that this Hermitian symmetric space geometry gives us a correspondence. This correspondence was stated like this and was proved by Roberto Garcia Prada and Gotten for these classical families of Hermitian groups. And it was a case-by-case proof, but they completely identified which was the group H dual as this non-compact dual of the isometry group. Nonetheless, there was no proof using that geometry. So what I'm going to show is how that goes. Let me, before starting, just say a comment about the generality of this work, because if we think about this symmetric space SP2NR over UM, we have considered the group SP2NR, but we could have considered also that joint form. And even we could have considered a 2-1 cover, this called metaplectic group. And this is not even a closed linear group, but it's also given the same symmetric space. And we could also consider a simply connected group given that symmetric space, and we have infinite groups given them. I'm only interested in the finite coverings of this adjoint group, because those are the group G such that I'll have a Hermitian symmetric space when I consider the maximal compact subgroup. So what I'm going to say is for all these groups in general. Okay. Now I'm going to say something about Hermitian symmetric spaces, some very well known facts. Let's start with the Cartan decomposition. And since the symmetric space is complex, we have the tension space. It has also now almost complex structure, and then its complexification is decomposed in the plus I and minus I parts, n plus and n minus. This will have a consequence on the Higgs field because we'll have these two Higgs fields. And moreover, we have that by the Killing form, n plus dual is n minus. If we take a maximal abelian subalgebra in H and we complexify it in this very special case, we get that that's a Cartan subalgebra, and we can consider its root system. What's special about this is that given a root, its root space is either on HC or MC. So we can talk about compact roots or non-compact roots, and we have a decomposition of this root system into compact and non-compact. Okay. Let's take the notation E alpha, E minus alpha, H alpha for this three-dimensional subalgebra corresponding to the root alpha. Let's take an ordering in the root system in such a way that n plus is generated by the positive non-compact root vectors. We define a strong orthogonality of two roots in that way, or simply saying that neither alpha plus beta nor alpha minus beta is a root. And it is proved that you can take a system of strongly orthogonal roots, positive and non-compact, whose cardinalities are the dimension of the Cartan subalgebra, which is in fact the rank of the Hermitian symmetric space. In the case of SUPQ, to put an example, this is simply as the complex subgroup is this one, and we have this complex structure. You can identify these pieces with HC and n plus n minus. Those elements, those system of strongly orthogonal roots, they correspond to these anti-diagonal elements here. With these elements, we can consider its sum, and then consider this E gamma plus E minus gamma, and then do the exponentiation of that element, and this is what is called the Cayley transform. This is a Cayley transform because via the Harishchandra embedding in n plus, it gives the usual transform between the Poincaré disk and the upper half plane. This was proved in general by Couragny and Wolf in 1968 that every Hermitian symmetric space has a realization as a generalized half plane, and they did it in general. I'm more interested in the action of this element on the Lie algebra. It happens that it has order 8, and this is the same to say that its fourth power has order 2, so I can decompose the Lie algebra into two parts, the plus 1 and minus 1 eigenspace. And more especially when it has order 4, this half plane I get, it's actually a tube domain. Tube domain is simply when you consider the complexification of a vector space you have in the real coordinates, the vector space, and for the imaginary coordinates you will have a cone. In this case it will be symmetric cone, and this, for instance, this half plane is a cone. Look that I'll always have in G, in every Hermitian symmetric space in this part GT, the adjoint action of the Cayley transform will be 4. So I'll always have in any space a kind of maximal cube subspace inside it, which corresponds to this part GT, and I'll have this the same for H and M. Okay. Now last slide about basics on Hermitian symmetric spaces. In the tube type case, we had that the fourth power of the Cayley transform is identity, so we can play the same game and consider the square of the second power, and we decompose H as H prime, the plus 1 eigenspace, and something else, minus 1 eigenspace. Consider its non-compact dual, which is obtained simply by taking this vector space and multiplying by I. this non-compact dual gives us non-compact the dual group. And if we consider the stabilizer of that element E gamma, it happens that the Lie algebra of that stabilizer is H prime, which is in fact the annihilator of that element. And the cone of the realization of the Hermitian symmetric space as a bounded domain of tube type can be written like H dual quotient by H prime, and is in fact the dual of the so-called Shiloh boundary, which is this complex symmetric space. Moreover, the adjoint action of this element E gamma defines an isomorphism from this isotropy representation M prime C, which is the isotropy representation corresponding to H dual, with this M plus pair, which lived in the isotropy representation corresponding to G, and this H prime equivariant, but we want it to be H prime C equivariant. Moreover, M plus has a structure of Jordan algebra in this tube type case. In general, if we don't have a tube type, we'll have a Jordan triple. By being a Jordan algebra, we have defined a determinant on it, and also we can define the notion of rank. The determinant of this special element E gamma is 1, and what happens is that the group HC, it acts transitively on the elements of M plus, which are of rank, maximal rank, and the isotropic group was H prime for E gamma. So what we get is that these regular, let's say, elements in M plus are this homogeneous space HC quotient by H prime C. Okay, so since this has been quite a lot of information, let me only pick up some facts, such as that I think this should, okay, there should be some things in red, but yeah, but in Spain we call red to another color. Yeah, I'm taking this H dual, and suppose this should be red, and this should be blue. Let's see what happened. Yeah, it's blue, okay. Yeah. Okay, now we are ready to go to the Higgs bundle setting. First of all, we are going to define Toledo invariant and talk about the Milnor-Boot type inequality. So consider the sum of these positive non-compact roots, and consider a multiple of this. That constant I'm putting there is that n is a dual Coxeter number, which is also what's called the genus of the Jordan triple, and which can be defined also from the restricted root system, that this gamma, these strongly orthogonal roots, you define a restricted root system, and by the multiplicities you can define also this constant here. Well, the important thing is that this element, which in principle it's an element of the dual of the Cartan subalgebra, defines a character in the algebra HC. And if we consider the degree of the bundle associated to this character, if the character does not lead to the group, if this is E is a HC bundle, if the character does not lead to the group HC, we'll consider a power, and then we'll take a multiple of it. And this number, this degree, happens to be the Toledo invariant. So if no one complains in the audience, we'll call this character the Toledo character. In the tube type case, it's very nice that it describes the semi-invariance of the determinant of M plus, because here remember that M plus was a Jordan algebra. We had an action, the isotropy representation of HC in M plus. So if we compare the determinant of this H acting on X with X, we have that the discrepancy is this Toledo character in H. Now, okay, yeah, okay. I should say that, well, if the character does not leave, well, we should put here some exponents, but for today we'll consider that the character, Toledo character, leaves without taking a power of it. Okay. What happens in any case, tube or non-tube, is that for any element of M plus, if we consider the kernel of the joint representation plus the image of the joint representation in the correct pieces to get something inside HC, this defines a parabolic subalgebra and a corresponding subgroup P. This is nothing special. In the case of SUPQ, imagine this M is this anti-diagonal thing, so the kernel plus the image is that. So you can trust me that it's indeed a parabolic subgroup. And we can do this in general for the Higgs field. So once we have the Higgs field, we can consider kernel of the joint representation plus the image tensoring by this inverse of the canonical bundle when necessary. And this will give us a reduction of our bundle to a parabolic subgroup, thanks to the fact that this quotient G by the parabolic is compact. And moreover, this parabolic subgroup has an antidominant character, which is written as a difference of two Toledo characters. I'm not going to say much more about this, because I think like 5 or 6 weeks ago it was Olivier Vicat who was here and wrote essentially the same. And that day he considered the polystability condition of the bundle. And then, thanks to the polystability condition, okay, let me stop it there. Thanks to the polystability condition, he managed to get a Milnor-Boot type inequality with that reduction this kernel plus image describes, and this character, which is the difference of two Toledo characters. You can get like this general form of the Milnor-Boot type inequality, but you can go further and plug into the rank of the Higgs fields. And in fact, you can go further and consider a parameter in the equations, like projectile flat connections, or this alpha polystability for alpha parameter, and you can get even a more fine inequality. But yeah, for today I will use only that one. And in the maximal case, the Toledo invariant is equal to this rank times 2G minus 2. And so this tells us that, well, this rank of the Higgs field is between 0 and the rank of the symmetric space. So in the maximal case, one of the Higgs fields will be maximal. Okay? So now we are ready to go to this general proof of the Cayley correspondence. I wrote this. Now this makes a bit more sense because I have defined what's the Toledo invariant. So what I'm considering at the left is the moduli space of polyastable G Higgs bundles with maximal Toledo invariant, and at the right hand side is the moduli space of H dual Higgs pairs, which are K² twisted. Okay. Well, I'm talking about polystability, but I won't define it because I want to focus on this Hermitian symmetric spaces properties. At the left-hand side, we have an HC bundle together with two Higgs fields, one for M plus, one for M minus, and at the right-hand side, we have an H prime C bundle where H prime was this stabilizer of that element E gamma. And we have a Higgs field which lives in this M prime C tensor the canonical bundle. I'm going to use some notation. Consider this fiber product, which is a principal HC times C star bundle. Well, K square. Yeah, it's K square. Yeah, it is. Thanks. Consider this isomorphism here between when I associate a vector space to a bundle, I tensor by the canonical bundle. This is the same that considering the action of this group on the vector space, where C star acts as usual. And now three things should become blue. Okay, so this one, yeah. So that's the change of notation I'm doing. Now, if I have maximal Toledo, I have said that this corresponds to having a beta of maximal rank. So if beta lives here, it will live in a subbundle of regular elements. And we had that these elements, these regular elements, were isomorphic to this homogeneous space here. So we are close to have a reduction from hc to h prime c. But the problem is that e power k is an hc times c star. So what we do is to modify this e power k, and we caution by the action of c star, and this action is diagonal on the center of the group hc, which, because this group is it comes from a Hermitian symmetric space, we know that the center is non-trivial, is non-discrete, and we quotient that with the other c star. And with this new bundle, we have that beta, it goes down, and we have a section of this bundle. And now e power k quotient by c star is an hc bundle, and if we change n plus by hc by h prime, we had that this is in fact the reduction to a h prime c bundle, and we have got the h prime c bundle we were looking for. Now let's go for the Higgs field. We had the determinant of the Jordan algebra. It's a polynomial of degree r. We had this semi-invariance of the determinant by the Toledo character. And now this defines in the bundle this determinant, which takes values in this bundle associated to the Toledo character. We can tensor this by k, so we obtain k to the r at the right because it's a polynomial of degree r. And since beta is of maximal rank, we have that the determinant is a non-zero section of that line bundle. That's the same to say that the line bundle is trivial, so the determinant it will take values in this trivial bundle. And what we are going to do is to polarize the determinant to get a linear map, an R linear map, and to plug into it the regular beta r minus 2 times. And this leaves two spaces there for these two n plus and n plus. But now we recall that n plus dual was n minus, so we can change this non-degenerate product we have defined from this multilinear map plugging beta r minus 2 times and get this isomorphism. And if we tensor by k squared, we have this. So now we are close to our Higgs field gamma. We call also that we had this HC equivariant isomorphism from n plus and n prime c, and this allows us to prove this result. Like here I have F, the bundle I have obtained. Now modify, well, if as I start with a Higgs field, which is a section of n minus, we can modify that isomorphism, tensoring by k squared. Now we have a chain of isomorphisms, and from this n minus tensor k, we finally get the Higgs field we were looking for. Okay, so, well, this is not all the proof, because we have to go first way back, and we have to care about stability issues. But the main aim of my talk was to show how to prove this correspondence in general. Somehow you take this maximal Higgs field and identify it with this element E gamma, because that's the element that in Hermitian symmetric spaces theory, it gives like the two pieces of information you need to pass from this side to that one, which are this isomorphism, which is changing the isotropy representation here and here, and this n plus regular to this homogeneous space, which is given the reduction. Now let me, to finish, say a word about what happens to non-tube type groups. Okay, these were also studied by Bradlow, Garcia, Prada, and Gotten, case by case. This corresponds for the classical cases, this SUPQ and SO star. And what happens is that from the reduction we have defined from the Higgs field, from the maximal Higgs field, together with the character, we get that this violates the stability condition of the bundle. So you get that all objects are strictly polystable, and in fact every maximal G bundle will reduce to this NGGT, which is the normalizer of, this is the maximal tube group in this case, but I refer to it before when I say this G equals GT plus G2. So normalizing that subtube, you get that that's the new structure group of your bundle. And what you basically get, up to some technicalities and a very little minor hypothesis, is in general that the modular space of maximal G Higgs bundles will favor over this space here, which are not Higgs. They are holomorphic principal bundles with this structure group right into the subtube and with topological class trivial, and that the fiber will be isomorphic to the these maximal GT Higgs bundles. Okay, so now, well, I think it's time to take a deep breath, and I hope you are glad we have finished on time. So thank you very much for your attention.
Questions? Really? So, any questions? Then we resume at 20 past 3, and we thank Roberto.